Thank you very much. The floor is yours.
Thank you for the introduction. My colleague and I are working together on the research project called LiDAR for HVAC, which is funded by the Austrian Institute called FFG, and today we're going to present our first results in object detection and instant segmentation of MEP components. Now let's dive straight into the topic. What you can see in this picture is our research infrastructure. This building is called the Living Lab Energeticum. From this building we have information from the design phase. We have a BIM model, the architecture, for example, but also the MEP components like the heating systems, the ventilation systems, which is very complex. Now let's have a look into the technical equipment room. You see all the different components like valves, pumps, pipes, tanks, and also an air handling unit here in the front. What we also have is information from a laser scanner based on point cloud information from this air handling unit, and this laser scan information is based on photo information like images and also free geometric information from the point cloud. Now actually it's very time consuming and a very manual effort for engineers to generate BIM model from laser scans. You have to do the measurement with laser scan, you have to prepare the data, do the segmentation, do the classification until you finally get the 3D BIM model. And the idea of this project is to make this workflow more efficient. So the idea is to have sensor-based reality capturing methods like LiDAR sensors to take the physical components. Then we use computer vision methods as a bridging technology to transfer this to a digital model and to finally have an as-is BIM model and this of MEP components. And this component or model can be used in different use cases, like to support retrofitting in the building stock, to support documentation, quantity takeoff, release of payment during the construction site, but also for predictive maintenance in the facility management, etc. So to reach this, to achieve these objectives, we have to first develop a computer vision workflow and take a component as an example. We decided to take the radiators as an example because it's a common component in MEP systems. It's visible and it has a simple geometry for objects to support MEP engineers in object segmentation. Then we wanted to check the performance of our trained model with existing deep neural networks. And finally, we want to identify the best trade-off precision and recall for our proposed application. How do we do it? We take the laser scan information as a baseline. Most of the research in this field is focusing on detecting the segments in the point clouds. Our research approach is focusing on the image. Then we take the deep neural networks for object detection and instant segmentation to identify the object in the image, and then use a pixel to point cloud transfer to make an overlap and transfer this information from the pixel to the point cloud, and you finally get a pre-segmented object, which then finally the user can decide if you skip it or confirm this pre-segmented object to make quality insurance. So it's very important for us to have the user integrated in this workflow. And finally, you can, all the instances which we confirm, you can use it for object counting, for quantity takeoff, for example, or using the as-is BIM model for further application, as we mentioned before. The workflow we developed is, first of all, we have to take many pictures, around 1,000 pictures of panel radiators and sectional radiators, together with our project partners. Then one expert has done the image labeling manually by polygons and rectangular forms for each image. Then we take the Solo V2 and YOLOx as a pre-trained deep neural network. We do the model training, and finally we test and evaluate the performance of these deep neural networks. And now I hand over to my colleague, Francois.
Okay. Thank you, Rainer. So I'll give you some
more details on our work. The database that we constituted has different radiator types, and it has over 1,000 images and more radiators, from 200 pixel to several thousands of side length. Here you see that 15% of the radiator masks the radiators are significantly hidden. The box is less than half of the mask in the box is less than half of the surface, and also 20% of the radiators are less than 1% of the image size. And we also had to take several control steps to ensure the quality of the data. How we selected the deep neural network for applying transfer learning, we chose an algorithm available in MATLAB, and also that handles different input image sizes, and that are good for also real-time applications. So for object detection, we selected the YOLOx, part of the You Only Look Once series, as well as for instance segmentation, the Solo V2, standing for segmenting objects by locations, which ensures a single stage identification without bounding box. We used COCO pre-trained network, and saved 10 to 20% of the data for validation and testing at least. Now how we evaluate the data with the precision recall curve and the detection threshold. And here you see the results for object detection, with the influence of the number of training images, which improves the quality up to 400 images, but we had failing training with 800 images in this case. The best model you see here with 400 images, and the influence of the overlap threshold on the precision to recall curve. And you also see the influence of the detection threshold from 0.1 to 0.3. Here, 0.1 ensuring the highest recall. Looking more in details in the characteristics of the images, which has been from the test database, we see here most of the correctly detected radiators as yellow dots with a very high confidence. Here, yes, in image 53, for example, we see also missed radiators, mostly from large images with over 3,000 pixels of side length, and also rather large radiators, like in image 119. And we also see false positive as black circles, rather small boxes. And here an example where the overlap ratio was too low. And yes, if we take a higher confidence as threshold, we have less wrong detections, less false positive. But if we want to have this this suggestion, image 30, we can also rely on user review to discard the wrong detection. So it's a balance to find. What's about the instant segmentation? You see here the also increasing quality with up to 400 images, and the best stagnation over this. The best model we have here with also very high recall and precision for the rather high overlap threshold, up to 0.8, let's say, which is a sign that the radiator mask, which is detected, fits well with the ground truth. And here the detection threshold, 0.35 here, ensuring the highest precision. You see here for this confidence threshold, the detection is rather good. With the threshold is the detection confidence is decreasing for small objects, more blue here. We have little missed radiators because of the shape here, for example, or also because of radiators that are significantly hidden. This is here in this lower part of the diagram, more than 50% hidden, some like this, and also the black circles, some false positive. You have here examples. If we would decrease the detection threshold, we see much more false positive, much more wrong detections. So to sum up the results, if in the end we can have a very high recall with our object detection algorithm, if we make sure that we don't have too large images, and we can also rely on user review to manage the false positive. For instance, segmentation, we should make sure the radiators are not hidden, otherwise they cannot be so well included in a BIM to scan-to-BIM process. And also the resolution should be enough so that the radiators are not too small in the image, not below 5%. So with this, we have a strong foundation for the forcing application, and we can extend the method to other MEP components, also trying to involve more semi-automatic labeling, and this will support the applications for takeoff and BIM and scan-to-BIM process in the combining LiDAR and computer vision for semi-automated as-built documentation. We'll continue in this project to enhance object recognition workflows of MEP components, including the BIM plugin for seamless integration of laser scan data. With this, I thank you for your attention, and we're happy to answer questions.
Very much.